Okay, good morning. So what we had, what we left off with was the Laurent series. I'm going to put that up. And I'm going to owe you a better proof of this. Actually, I proved the first half of it last time, but I want to get to the applications. So here's what we have. This is called the Laurent series. And it's like a Taylor series, except not only does it have all the positive powers, it has all the negative powers as well. Okay. So what we have is for a function that we can do a series expansion for, we'd say we have a sub k z minus z naught to the kth power. Right? And the Taylor series goes from k equals 0 to infinity, so we're used to that. But the Laurent series includes the negative powers, so we're going to say k goes from negative infinity to positive infinity. And we had for these a sub k, and I showed you the proof for the Taylor expansion. For the positive powers, negative powers, the proof is very, very similar. So a sub k 1 over 2 by integral f zeta d zeta zeta minus z to the n plus 1. Z sub 0 to the n plus 1. So yeah, you know we have some z sub 0 there. This is the, we're going to draw, we did concentric circles, so we'll just say we have a circular, arbitrarily small contour around z sub 0. That's what this is here, C, proper orientation. We showed it for all of the positive powers, and that it extends for all the negative powers as well. Okay. And by virtue of this, we were able to show that if a function has one derivative existing, if it's analytic, it has infinite derivatives. So that's much stronger than what you have in real analysis in terms of differentiability. If you have true differentiability to the first degree, then you have it for all orders. Okay. So good. That's called the Laurent series. You've got all integer powers. And now I'm going to, and I gave you a couple of examples. They were very basic, but when I started with negative powers. So now I have to give you some definitions. So this is going to be called classification of singularities. Classification of singularities. So tired. And what do we have here? First thing, we're just talking about poles. And we have f of z. No, there you go. F of z, a negative m, z minus z sub 0 to the n. And we'll just work our way up. Negative n minus 1, z minus z sub 0 minus 1. So this here is just the name. Okay, that's just the label of that coefficient. Work your way all the way up. A sub negative 1, z minus z sub 0 plus a sub 0, and so on. Okay. So if our expansion, for a Laurent expansion, looks like this, and this is the highest order pole, so we'll call it Z sub 0 a pole of order M. Mth order pole, that's just the inverse power of the pole there. The second definition we need is of a removable singularity. So if you can remove a singularity, we have f of z is not defined at z sub 0. You know, it could be one of these poles. Defined at z sub 0, but limit z goes to z sub 0, f of z exists. So it's not defined, but the limit exists, and the simplest example of that would be sine of z over z. So let's write f of z equals sine of z over z. Because this is one we've worked with before. F of z equals sine of z divided by z. Because you can't just plug in z equals 0, right? That doesn't exist. On the other hand, you know your Taylor expansion goes z minus z cubed over 3 factorial, z to the 5th over 5 factorial, and so on. And when you multiply that out, you get 1 minus z squared, etc. Right? So that's well behaved and well defined. So that's a removable singularity. And the third one, do I have room to write that in here yet? Essential singularity. It's not removable. Essential singularity. I'm just going to do this example. E to the 1 over z. Okay. So what's e to the 1 over z? That's not a finite ordered pole, and it's not removable. Because remember, your exponential function, you would have 1 plus 1 over z plus 1 over 2 factorial 1 over z squared. Now you're just going to have all orders of 1 over z. So that's an essential singularity. Okay. And then we need, so this is what we're going to be working with. Poles of order M, and we're going to see in a minute, this is the absolute key one here. This one is the one we've been working with. Now I have to define the residue for you guys. And then we can get all of our interesting results here. Still doing some definitions. So what is the residue? So let f of z again be analytic in and on closed circle. C except at z sub 0. So we're just going to be on a circle. There's our z sub 0. We're analytic everywhere but there. Then we can write down what I just erased. We can write down the Laurent series. Okay, we've got our base of k. Z minus z0 to the k. Now we're going to do the integral around that circle. And integral f of z dz And I'm just gonna write out what it is. That equals 2 pi, there's the I, that equals 2 pi I times a sub -1. And the way we get that is just by integrating this expression here term for term. Because all of the other powers just gave you 0, we did that earlier. And only this one power, this first inverse power, gives you a contribution. So T 2 pi I a sub -1. I have to erase this stuff right here. So integrate this thing here, star, by term. And use this back dz z minus d0 to the n is equal to 2 pi I if n equals 1, 0 otherwise. So that's what we've done, and you should actually look at that calculation again to make sure you see how that goes. I think we've actually done it a couple times now. This is when you go, a circle around z minus z 0. So that's all we did here, right? We had all those infinite positive and negative powers potentially, and the only one that gave contribution was the -1 power. So that's why it's a sub -1. And actually, I'm going to go ahead and write up the integration expression for the coefficients. So we'll also note that this a sub k, which was 1 over 2 pi I integral f of z dz z minus z naught to the n plus 1 does the same thing. It gives you the same result when you have n equals -1. This goes away, it's just f of z dz around there. You get 2 pi I in -1. Okay. So this result here is in this definition as well, built into that definition as well. So all right, also contains this result. Result for n equals -1. So now we can define the residue. The coefficient a sub -1 is called the residue. A sub -1 is the residue. The residue of that function at z sub 0. Now we're just going to go back to what we've done before and prove the residue theorem, because suppose in this picture you have a bunch of those singularities, then the integral around the outside is going to be the sum of all of those residues, and that's actually the residue theorem. And I can put that right here, and this is going to be our tool to do a bunch of these integrals comfortably. So the residue theorem. And F Z analytic in and on the simple curve C, which is really that similar type of picture, comma, except for a set of Z sub K, Z sub whatever, Z sub J inside there. So the picture that goes with this, we'll make this one big enough. We have a collection of points where we have, where it's not analytic, you know, by implication, these are collection of poles. Okay. Collection of poles there. And the residue theorem is going to say that this integral, put it down here at the bottom, then f of z dz around that closed curve, c, which is this one here, properly oriented curve around there, is equal just to 2 pi I times the sum of all the residues at those poles. So we'll say sum of residues f of z sub k and the sum of these singularities z sub k. So there's the theorem formulated. And what you'll see is that the problems that I posed before where we had more than one pole, it was essentially the residue theorem. Okay, we're just counting them up. That's why it was 2 pi I, you go around one, you go around the other, and so forth. So the proof of this thing is really the discussion we had before. Originally, we go in here, circle, go back out, and then continue on our way. Proof by circle, right? And you're always clockwise around those poles and you're canceling those things there. So I've drawn enough of these. And because you're always clockwise, if the whole thing equals 0, then the outside contour equals the sum of the inside contours if you just reorient them to the proper, you know, counterclockwise orientation. So there's your proof. So you can say that's already what we had before, right? We could have actually said the same thing earlier. What we gained though with the Laurent series is there's techniques for calculating more complicated ones, or some difficult ones that we couldn't calculate yet. Okay. But yeah, this is basically the way we already were looking at the problem. Okay, so that's not new in that sense. What's going to be new is that we'll make use of the Laurent series of the fact that we have some statements about these infinite series of those inverse powers. Good, so let's make sure. Yeah, and then an interesting point, or important point here, what you have to do, if you're doing this systematically now, you have to have your Laurent series at each point. Right? At each point you could, and you'll see, we do it once we actually have the whole thing for most of our problems, but fundamentally you have to get your Laurent series at each point and then pick off the residue, the a sub minus 1. So let's go ahead and write that down. So at each singularity, expand f in the Laurent series. And then pick off the a sub minus 1. So here's where we get a rule that goes beyond what we had done before. So I'm going to erase this. And we will learn what to do with higher order poles. So here I'll give a little discussion of some properties of the residues. So first of all, just to repeat myself, residue equals a sub minus let z sub 0 be a simple pole. So first order, n equals 1. So I have here a sub n equals 0 for all n less than minus 1. Okay, so a simple pole just has the kind that we've been working with so far. Then our residue, here, capital F, capital R. Okay, so then residue capital C sub 0 is the following. Limit as z goes to z sub 0, c minus z sub 0, f of c. So you'll see as soon as we do our examples that we've done before, this is what we've been doing so far. Okay? We've been doing this, and by saying limit, z minus 0 times f of z, that's the one we canceled. Okay? But now if we have a higher order pole, we get something new. So pole of order m, and I'm just gonna write this. What I'll do is I'll give the rule and then I'll have some room to. What we're looking for, the residue a sub minus 1 is equal to 1 over m minus 1 factorial. The m minus first derivative of c minus z sub 0 to the n f of z. There's the rule at z, limit z goes to z sub 0. Okay, when m equals 1, then we go back to exactly what we had here. In case m equals 1, we're back to this one. But higher order poles, we use this expression. And I'll show you how that works. Let's write this out. We have f. In fact, all we have to do is carefully write this out and ponder it. So f of z equals a sub negative m z minus z sub 0 to the n plus a sub negative n minus 1 plus, and then all to this crucial one, a sub minus 1, z minus z sub 0, a sub 0, plus and so forth. So we're just looking at the negative powers. So let's look what happens if we multiply this by z sub minus z minus z0 to the nth power. Okay. What we're trying to do is, here, let's make sure I write it. We're trying to extract this thing right here. Okay. And we multiply by z minus z0 to the nth power as per this expression here. And here we just have a sub minus m. Here we have a positive power. Here we have z minus 0, z0 to the m minus 1. Right? By doing that multiplication, this one turns into z minus z sub 0 to the m minus 1 becomes a minus 1, right? And after all, this is the one we want. And now if we take n minus 1 derivatives, each one we take, is going to generate the n minus 1 factorial. And we take n minus 1 of those derivatives we're done. And all that's left over is a sub n minus one. So this is nice. You don't actually have to do some big expansion here. You actually have to just take the function, if you see that it has that order of pole, multiply this, take a couple derivatives, and see what happens, okay? So this is the reason. So we need to isolate a sub -1. So I'm gonna leave this up here. That's the rule. And that's going to take us into a whole bunch more interesting calculations. So let's see here. And there are other rules. We're going to leave those. This is, no, I have one more. I have one more rule, and then we'll apply. Okay, one more rule. So we're going to hold on to this one. Hold of order M, and this was the proof of that, the demonstration of that. And another one that can come up pretty often is a quotient. These are the functions that come up most often in the applications. So suppose we have P of Z and Q of Z analytic. Z sub 0 and Q of Z as a first order pole. Oh no, not a first order. Q of Z sub 0 is equal to 0. And what we're looking for is f of Z equals P of Z divided by Q of Z. So yeah, we've got quotient function. This one vanishes at Z sub 0. This one does not. So what we can do is just write what their respective expansions would be. So this would be P of Z sub 0 plus, all right, P prime of Z sub 0, Z minus Z sub 0 in higher terms. And this one would be Q of Z sub 0, Q prime of Z sub 0, Z minus Z 0 in higher terms. But remember, this one is equal to 0. So this one starts right here. So if we have that form, what we'll do is we'll pull out a 1 over Z minus Z sub 0 in the following way. So we'll say we've got P of Z sub 0 So I'm going to pull out a P of Z sub 0 divided by Z minus Z sub 0 in the numerator plus P prime Z minus Z sub 0, so on. In the denominator, I'm pulling out a Z minus Z sub 0, so I'm starting with Q prime of Z sub 0 plus the higher terms. And so what's going to happen as we take the limit, Z goes to Z sub 0, we're going to have a P of Z sub 0 divided by Q prime of Z sub 0. Because these higher terms are going to get arbitrarily small, and this is the one's going to dominate with the Q prime of Z sub 0. What we get is f of of z approximately p of z sub 0 q prime of z sub 0 times 1 over z minus z sub 0, right? Plus higher terms. But that means we'll have a simple pole, essentially a simple pole with the coefficient p over q prime of z sub 0. So that can turn out to be our a sub minus 1. Therefore, residue f of z sub 0 is equal to p of z sub 0 q prime of z sub 0. So that rule is easy to apply as well. And it can be generalized to higher orders, but it just gets more complicated. This is a good one to stick with here. No, I suspect this one is off the screen. So I'll just put the result right here. So residue f z sub 0 is p divided by q prime of z sub 0. So that's where that comes from. Good, so that's our fourth rule. Now let's, for fourth part of this, let's do an application, or 2 or 3. So we'll look at one that we've done more than once, and we'll look at one that we haven't done. And actually, I'm going to keep this rule up here. Here's the two examples. This one, of course, we've seen repeatedly. 1 over z squared plus 1 dz. The second one, we're just going to square that. So suppose we have z squared plus 1 squared dz. We didn't have the technique to do this one so far. And yeah, say we wanted this thing from minus infinity to plus infinity on the real axis, the way we've done before. So what we're looking at is 1 over z plus I, 1 over z minus I, go ahead and write it that way, dz. And if you look at this rule here, for the first order pole, by the way, let's go ahead and remind ourselves. We have a pole at I, that's this, and we have one at negative I, that's that. So what are we going to have here? And we're going around the pole. And in fact, of course, we want to go over the whole infinite plane, but we're just taking what the theorem tells us. So it's going to be lim 2 pi I So we're going to have 2 pi I, and now we're looking for the a sub minus 1. It's going to be here, so we're going to take limit z goes to I, z minus I, 1 over z minus I, 1 over z plus I. And that's where the z minus I cancels. 2 pi I, 1 over 2I equals pi. Okay, so that one we've done before, and that's just the rule there now, so that's nice to see. This is the one that brings something new into the game. So the second order, notice we have the same situation. We have poles at I and negative I. This time we'll be a little more careful. So we're going to circle the upper pole. There's our integral that we're doing. A little more careful. And what we have here is integral 1 over z plus I, z minus I squared dz. So we have those second order poles. And since we're circling the top one here, I'm going to go ahead and write, we have dz z minus I squared z plus I squared. That's the one we're doing. And we're going to circle this one here, z equals I. So now we have 2 pi I. And we have a second order pole, okay, at z minus I, so we're going to have times 1 over 2 minus 1 factorial, so that's still just 1. Okay. We have d over dz, second order pole, and minus first derivative d dz, z minus I squared. And then there's our function, z minus I squared, z plus I squared. Take the limit there. So these cancel. And we're looking at 2 pi I d over dz 1 over z plus I squared, and then z equals I. So we'll get this one here. And we'll take it continuing on to 2 pi I. Now the derivative, we got minus 2 z plus I to the third. We have to evaluate that at z equals I. So that takes care of the derivative 2 pi I minus 2. And we have 2 pi I negative 2. And then we have I plus I, which is 2I to the third. And we have 2 I negative 2. And we have 2 squared times 2, and I cubed is negative I. So when all is said and done, we're going to be left with rid of the 2's, minus sign, i's, and we're left with pi over 2. There's one we could not have guessed. Now you can see what I'm going to do for the assignment. We're going to do a higher power still. Okay? And we don't want to go too high because that just gets tedious, because taking these derivatives, you know, is not bad, but still, you know, you got to do some derivatives as well. Okay? That's what we're going to put on the list of problems. I'm just going to put a bunch of interesting problems up and we'll start looking at them. And we already had a couple for next week, so let's see how far this takes us here. Good, so there's that rule. We can go ahead and erase this board for the moment. And yeah, I want to assign some of these, but then I want to talk about the actual physics applications of this technique. Which we already touched on. So let's go ahead and erase this. make this list, we'll call them homework problems, and then we'll see how far we take this. Homework problems, we already have a couple for this, or what do we have, one for this week or two? We had one so far, yeah. So this one, enumeration, we're looking for minus infinity to plus infinity dx x squared plus 1 to the 4th. That's right, I went there, okay. 4th power. So now you'll have to take 3 derivatives, and you can meticulously work your way through that. Another interesting one here. So minus infinity plus infinity x cubed sine of x dx over x squared plus 1 squared. And you'll notice we have the two odd functions whose product is an even function. But we have that pole, that second order pole here. I'll give, actually I'll give a good hint on this one. This is similar to what we did before. If we put the sign of z as e to the iz minus e to the negative iz, right, over 2i. If we do that, we're actually going to have to complete the integral in 1/2 plane for one integral and one for the other. So instead of that, we can just call this the imaginary part of x cubed e to the I x dx. And then I'll have x plus I squared, x minus I squared, factoring this one out already, just the way I did before. If you do this, you use the residue theorem on this thing, then you take the imaginary part when you're all done. It'll probably only have an imaginary part, by the way. You take the imaginary part when you're all done, and you get an interesting result, okay? The third one I want us to talk about is, do this one. We'll do an easier version of this first one here. So we'll do dz z squared plus 1 cubed. In fact, you may want to do this one first. We're actually looking for it, the value on the real axis. But again, we have higher order poles, and this one needs 2 derivatives, this one needs 3. So this one, start with this one, give it a try. Start with the one I did. Do this one, do this one, and you got that pretty straight away. So the other problem, though, that I want to talk about now, here we got plenty of time. Suppose we have f hat of k, 2 alpha root 2 pi, 1 over k squared plus alpha squared. And we want to find the original function. So this is actually getting the application to be close to physics. Okay? So what is this here? This is a Fourier transform. That's why we're calling it f hat of k. Find f of x. Where x, actually, f of x such that negative infinity less than x less than positive infinity. X less than positive have to start using some of our techniques. This is going to be a simple enough one in terms of the residue theorem, but let's write down what f of x is, and then we'll see what the problem is. 1 over root 2 pi f out of k e to the I k x dk. We're using the letter k instead of the letter z, right? But otherwise everything's the same. And we know this goes from minus infinity to plus infinity. So yeah, let's see if you can go, no, can't resist. So let's talk about this a little bit more. 1 over 2 pi. We'll go ahead and plug in what we have here. So we've got 2 alpha, the root 2 pi, the 1 over k squared plus alpha squared, e to the minus ik, no, plus ikx. That's important. dk. So far so good, minus infinity to plus infinity. But now we see we're going to use the residue theorem to solve this thing. So where are the 2 poles on this guy? Where are the 2 poles? You know, factoring out this denominator again. Different letters, same idea. Anybody? So we can say k squared plus alpha squared, k plus I alpha, k minus I alpha. So it's no longer x, k and alpha squared. So I didn't say it was real, but I meant it. So here they are. They are here, and we're actually on familiar ground. So we've got I alpha minus I alpha. Here's where it gets interesting. We haven't been doing these integrals so much with this, but we got a little bit right there. But see, we have k as our complex integration variable, and x is just playing the role of a parameter. So if x is positive, we've got one curve, one Jordan, right? Remember Jordan's lemma, and I assigned the bottom, I assigned the 2 different lines. So if x is positive, you're going to complete the curve with one of these, and if x is negative, you have to complete the curve around the other one. So that's the important lesson on this. That comes up in applications a lot. You know, we're looking for an f of x, and we want to have it across the entire real axis. So you have to do a different, and look up Jordan's lemma at that point. You have to do a different contour for positive x and for negative x. So that's what I'm going to put here as a note. And this result will turn into a very simple, recognizable result. So that'll be kind of fun. In fact, something we've worked with before. So choose contours carefully. X greater than 0 and x less than 0. You'd say, you know, you think you're just looking at the same function, but they have a different contour. You have to close around the top and the bottom. Have different contours. And we're using the fact that, you know, this contour vanishes and we're just getting the real integral the whole time. The integral over that contour vanishes, and the integral over this contour will vanish. We just have to see which one it belongs to, x greater than 0 or x less than 0. And I'll leave that detail up to you guys, that's an important one. So this takes us pretty close to some applications, some physical applications. I think I'll even jump into that too. But for next week. Actually, no, I think I'm just gonna set this one. So let's see, we have a number of different applications. Okay. Yeah, it should be clear enough, right? This is the factorization, your function, you know, is the whole thing, but in particular, it's this part here. So C. Jordan's lemma. Okay. That'll do it. Okay, so here's the thing we're gonna work on next week. I'm just gonna set this up. So, who recognizes this differential equation? All right. In 105A, we've been working on it. And, you know, f of t over m. And what we're going to do, I'll get this out again. Omega naught squared x equals f naught over m cosine. I have to use a different letter omega because the other omega is taken. Okay. So we want to solve this using Fourier techniques. Solve using Fourier integrals. You know, because we've seen the solution of this before, this is not going to be easy, but it's going to be really instructive. And we'll take it most of the way till we get a really clear picture of what's going on. But if we're going to solve this using Fourier integrals, the idea is we're going to have, you know, x of t is going to be 1 over root 2 pi integral x hat of omega e to the I omega t d omega. So we're going to rename these things. Instead of k and, you know, k and x, we're going to have omega and t. And x hat of omega is going to be 1 over root 2 pi x of t e to the minus I omega t dt. And then, you know, standard boundaries of integration. So we're going to do that, that's an infinity. We're going to do this step by step. So, and these are kind of applications you get in quantum mechanics, a lot of, right? Talking about things in their Fourier formulation. So this will be a perfect start for that. And because we know this pretty well, we'll be able to make sense of everything that we encounter. So that's where we're headed. And actually, I'm going to add one thing to it. I'm going to erase this. We're also, right, because we have this function on the right, we're also going to have to do the same thing for the function f of t. So there we have f of t, same formula, 1 over root 2 pi f hat of omega yeah, hopefully when we tackle these, we'll have enough experience with the homework problems. It'll make sense. We do have, we have to switch gears with the name of the letters. But this will give us a lot of interesting practice, okay? The right side here is going to be given to us. The left side we're trying to find because it's a differential equation, right? Fundamentally, a mystery on the left side, and we're given the right side. But because we know the solution to this, we'll be able to make contact without any problem. Good, so that's where we're headed. And a couple applications like that, so then we'll have a good view of this. When we get back to linear algebra that touches quantum mechanics, we'll actually just have these in our arsenal. Write it down. Good, that's the plan. That's all we've got for today. So I think we have plenty to work on. So when we meet next week, we can tackle some of these integrals I just had on the list there. And resolve all